Hi, pre-calculus students. In this video, we are going to be looking at section 5.1 on quadratic functions. Now, you've all seen quadratic functions before, so I hope this is a review for many of you. What you'll see here is section 5.1. I hope you were able to print out the notes. If you weren't, you can certainly take them down on your own without printing them out. But here we're looking at quadratic functions. So there are several forms of a quadratic function that we'll start with. But first, let's do the definition. So a quadratic function is a polynomial function of degree 2. The graph of the quadratic function is a parabola. Now, the general form of a quadratic function, that's what you see most often, is f of x equals ax squared plus bx plus c, where a, b, and c are the coefficients, but they're also real numbers, and a does not equal 0. Now, of course, the reason a can't equal 0 here is because if a was 0, you wouldn't have an x squared term. Continuing on, the standard form of a quadratic function is a times x minus h squared plus k, where a, once again, can't equal 0 or you wouldn't have a quadratic function. Now, this form is also called the vertex form, which makes a lot more sense to me to use because it gives us the vertex of the function. So if we have the function in this form, we know that this number here, if it's being subtracted, is h, and it is the x-coordinate of the vertex, and k is the y-coordinate of the vertex. So another way we can find the vertex h and k is by using the general form and this formula. H, the x-coordinate, is found by taking a negative b and dividing it by 2 times a, which you have as the coefficient of x squared. The y-coordinate is found by, once you get that number, you plug it into your function, and that'll give you the y value of the function, and you will have your vertex. Let's look at the different parts of a quadratic function when it's graphed. So a quadratic function graphs a parabola, as you may know. The vertex is hk if you put it in vertex form, but if you have to figure it from the general form, it's a negative b over 2a, and then you plug that into the function, and you get the y value for the negative b over 2a, and that is the vertex right there. In this case, it looks like our vertex is 1, negative 4. Now, the axis of symmetry is the vertical line that goes through the vertex. The axis of symmetry is always of the form x equals some number, and the number that it equals is the x number. So in this case, my vertical line crosses the x-axis at 1, so the equation of the axis of symmetry is x equals 1. It, of course, can be found by doing x equals a negative b over 2a if you're in the general form of your quadratic function. Now, your x-intercepts, we'll learn later, can be found by setting y equal to 0, or f of x equal to 0. And your y-intercept here, which looks like it's 0, negative 3, is found by letting x equal 0. So I'm just going to do arrows here. Let x equal 0. Those are some major parts of your parabola. Now, the nice thing about being able to find, for example, your y-intercept here or one of your x-intercept is that you can go across the axis of symmetry in equal distance and find a couple other points on your parabola. So that's really handy. Another thing to note about your quadratic function here, and you probably already know it, but if this number a, either in the general form or in your standard vertex form, if that number is positive, then your parabola opens upward, like the one we have here. So if a is positive, then the parabola opens upward. like this, and your vertex is a minimum. If A is negative, then your parabola opens downward. Like this, and your vertex would be a maximum, an absolute maximum. All right, so how do we convert between the two forms? It's very useful if we are able, to convert between the two forms, the general and the standard form, or the general and the vertex form. Well, we do that by completing the square. So to remember how to complete the square, we're going to do a little crash course in that skill. Let me take you to a different page. In order to convert from standard to general form, we need to know how to find perfect square trinomials. Perfect square products or patterns of quadratic functions. So let's look at what perfect squares are. A perfect square is a number, of course, like 9, because it's the same thing as 3 squared. Or maybe a number like 64, because it's the same thing as maybe even a negative 8 squared. But these numbers are perfect squares. So if we look at perfect square patterns of trinomials, what we want to be able to do is take that trinomial and turn it into the binomial that created it. So if we had x plus 1 and you square it, what you're going to get is this x squared plus 2x plus 1. What we want to be able to do is start here and go back to here and figure out what perfect square created that for us, what binomial squared created that for us. So we look for patterns. So when we multiply a binomial by itself, what happens is that the middle terms are always the same. And there are 2 of them. So if you take 2 times the middle term, you get this middle term. And that's what happens if you just look at the numbers in your binomials. So here, for example, if I go down to this perfect square pattern and I look at that number was 2 times some other number. And of course, it's 2 times 3. So 3 was the number that was here to create that perfect square trinomial. Now, this number also then gets squared to form the 9. So let's write that here. We took, trying to get different colors. We took 2 times 3 to give us 6, and 3 squared gave us 9. And all of these perfect square trinomials follow that same pattern. So if we started with this perfect square trinomial, if we took this number 8, a negative 8 actually, and divided it by 2, and then squared it, that gives us this number. Negative 8 divided by 2 is negative 4. Negative 4 squared is a positive 16. And this negative 4 was the number that was used in our binomial. Then we have some other patterns here to confirm, or some other perfect square trinomials here to confirm that pattern. If you take this number 10 and divide it by 2, that gives you the 5. And it's that 5, the 10 divided by 2 is 5 squared, that gives you this term. So looking here, it's a negative 12 divided by 2. That gives us, if you square it, it gives us the 36, which goes there. And this negative 12 divided by 2 was the binomial that gave us that perfect square pattern. So I hope you can recognize that from things that you may have done in previous courses. So let's see if we can figure out the missing pieces here. Here we have x minus 3, so that means this number divided by 2 gave me 3, so it must have been 6. And this number squared gave me my last term, which is 9. Let's do it with this perfect square trinomial. If we take this number 16 and divide it by 2, we get 8. Squared gives me the 64. And it means that this number inside here, the 16 divided by 2, was the number at the back of the binomial. And the signs correspond to the middle term. So here, this x minus 3 is a negative 3 because my 6x was negative. Here, this is a positive 16x, so this is a positive 8 in the binomial. Back here, we're going to take that negative 22 and divide it by 2. Gives us a negative 11. And a negative 11 squared is the 121 that goes here. And the negative 11 is the number that goes in our perfect square, in our binomial. That's how these perfect square trinomials work, and it's advantageous to be able to recognize that pattern as we look at completing the square. So let's go back to our notes. In order to convert between the two forms, we are going to use that completing the square. And this is how it works. So if we look at A, we have h of x equals 2x squared plus 8x minus 10. Now, what we're going to do is we're going to take our first two terms with the x's and we're going to group them together. So we have h of x equals the 2x squared plus 8x. And I'm going to dangle my constant term out here, my c. Now from this one is a little, it adds an additional flavor to it because we have the coefficient of x squared here. What we need to do if we have a coefficient first is to see if this number can be divided out of the first two terms. And in this case, it can. So if I do that, if you divide the 2 out of 2x squared, you will have x squared left plus 4x. And once again, I didn't leave enough room here. All right, we're going to leave a little more room for a trinomial there. And then we still have our negative 10 dangling out here. Now we want to complete the square of what's inside my parentheses here. So we know that we take this number and we square it. So 2 squared is 4, and that's what gets added inside the parentheses to complete the square. However, I really, on this side of my equation, I added 2 times 4. So I really added 8. So in order to keep this equation balanced and not weight this side with an extra 8, we're going to subtract the 8 from the same side. It's just the process we use to complete the square. Now we can identify what we have in the parenthesis here as the perfect square binomial x plus 2 squared. So these three terms are the same as this binomial squared. And back here we have minus 18. And ta-da! We did it. Ta-da. We've put it in vertex form. So according to vertex form above, this tells me that the vertex of my parabola is a -2, -18. And that's all we had to do on this one. Now we can confirm that. So let's check it. If you recall, the way to find this without putting your quadratic formula in vertex form is to find your vertex by taking a -b over 2a from this form and then substituting that into the function. Since this is an h function, we're going to substitute it in to the h. So let me show you what I mean. A -b over 2a here would be -8 divided by 2 times a, and a here is 2. So this is a -8 divided by 4, and a -8 divided by 4 equals a -2, and voila, that is indeed the x-coordinate of our vertex. Now we simply plug that in. What this notation means is you plug the -2 into your function to get your y value. So we're going to do that. We'll plug a -2 in here and have 2 times a -2 squared plus the 8 times -2 minus 10. All right, this is going to give us, this is 4 times 2 is 8, minus 16 minus 10, which is 8 minus 16 is a -8, minus 10 is a -18, and voila, that is indeed our y coordinate. All right, let's try part B here. On B here, we also want to convert it into, use completing the square to convert it into vertex form. I want you to pause the video and give it a try. I'll stop the video here and then we'll go through it together. All right, so the first step that we take when we're completing the square is we separate the constant term and we move it away. Then if we have a coefficient of x squared, which we do once again here, we factor that out. And if we factor the 3 out of 3x squared, we're left with x squared. And if we factor the 3 out of a negative 6x, that would give us 2x. We're leaving a space here, and my 9 is still dangling out by itself. Now to complete this square inside here, we go, okay, we take this negative 2 and we divide it by 2. That gives us a negative 1, but we square it. And if you square a negative 1, you get 1. And that is the number that we add here. You square a negative 1, you get 1. That's what we add here. But what we really added here was 3, because this is 3 here is being multiplied by this 1. So in order to keep this equation balanced, we subtract the 3 at the end. Combining these two numbers, we get a negative 12. And we recognize this as a perfect square trinomial, so it's equivalent to the x minus 1 squared. And thus we have completed our task of putting this into standard form or vertex form. Now from this, of course, we can get our vertex, which is the opposite. The x is the opposite of this number, so it's a positive 1. And the y value of my vertex is that negative 12. Now, if we check it using the formula, to find the x coordinate of our vertex, we take a negative b over 2a. So a negative b would be a negative 6. So that's how that got here. Over 2 times a here is 3. So this gives me a positive 6 over 6, or 1. Notice that's the same number that we have for our x coordinate of our vertex. Then we substitute that 1 in. That's what this notation means, and you get negative 12. So we know we've done it right. In our next video, we will try a couple more problems from section 5.1. Thanks for watching.